Welcome to Module 47 and Logistic Regression and Error Metrics. So ideally, at the end of this module, you ought to be able to explain how logistic regression maps feature vectors to probabilities for a binary outcome. You ought to be able to relate the logistic model to linear regression via log and odds and the sigmoid function. You ought to be able to implement a simple logistic regression classifier in scikit-learn. There's only a few lines of code. You ought to be able to compute and interpret core classification metrics, or at least understand them. And you ought to be able to diagnose when accuracy can be misleading. We talked a little bit about how accuracy can be misleading in module 46, the previous module. A lot of the same concepts from regression apply to classification as well. And we'll talk a little bit about connecting these predictions in terms of their thresholds, which a lot of these concepts are yet to be introduced, so let's dive in. So I kind of hinted in the end of the last module that, I asked you to think a little bit about how some of the concepts related to regularization and scaling might generalize from regression to classification. So in regression, our target is like a continuous number, like the tip percentage we saw in previous modules, or blood pressure, on a scale. And we had ordinary least squares, or OLS, and some variance to perform that kind of prediction. And then once we, at least to make a model, once we have that model, we can evaluate how good it is using mean absolute error, or root mean squared error, or we can look at plots, et cetera, et cetera. Classification can take many forms. We often focus on binary classification just because it's very simple. You're either yes or no, true or false. So we have two categories. It could be sick or healthy, or fraud and not fraud, up or down, pass or fail, and so on. So we still care about probabilities. So statistics and probability is like fundamental to everything we do in machine learning and artificial intelligence. If you learn only one thing, if you can come away from this class with one kind of, not even piece of knowledge, but like a strategy or a frame of mind with which to approach AI and machine learning in the future, it's that probabilities are fundamental to everything, and you need to learn how to think properly in terms of probabilities and statistics, and apply that to all of the very careful, curious scientific mechanisms around the use of probability. So it's going to be really important. We're going to be given some inputs x, and we want to say what is the probability of our prediction y being the positive class, given x. And you'll remember that this is the form that this little expression takes. What is the probability of positive given x? And we're going to basically learn the probability function using machine learning in order to make these kinds of assertions as accurate as possible. But I think I'll get into a little bit about the difference between like a probability and a decision. So a probability is sort of just a rough kind of estimate of the of how likely something is. But we want to make decisions. Classification in practice is all about taking some inputs and then deciding whether or not to label this as class 1 or class 0, as positive or negative. And the easiest way we can do this is just to have a threshold in terms of our probabilities. And we can set this threshold to 0.5 arbitrarily for now. And we can say, well, if the probability of the data point belonging to class 1, if the probability is above 50%, then we can say it's class 1. And if the probability that this observation is class 1 is less than 50%, then we can say it's class 0. Okay? I'll say that again just to make sure you get it. I'm trying to say what is the probability that this is a positive case that I'm looking at. This, given the input x, does input x belong to a positive class? If the probability of it being positive is 51%, I say yes, it's positive. If the probability of it being positive is 49%, then I can say no, it's not positive. This is very crude, obviously. There's a difference of 2% between a positive and a negative decision, but that gets the whole process started. So we'll start from there. So logistic regression, as the name suggests, is like it's an offshoot of regression. Under the hood, it's going to look very much like regular old regression. But it'll be used to make predictions on a binary case, and we're going to more or less estimate these probabilities. So logistic regression will be a way to generate probabilities. Given a feature vector x, we're going to produce the probability, and then we're going to use this probability with a threshold to make predictions. So why can't you just use linear regression? We already know how to do linear regression. Why don't I just take all of my data? I have my x's, I have my y's. I can fit a straight line, or a straight line, or a hyperplane in many dimensions between my inputs x and my predictions y. And I can also have a threshold in that space, and I can just use linear regression for that purpose. So remember, linear regression had this form, and now previously we called W beta because that was sort of common in a lot of the reading material, but in machine learning parlance, same idea, beta is now W. So we want to learn some parameters W that we multiply with x, and then we might have a bias term b, which is another one of the betas we were optimizing for before. And then this is a linear function. This is like linear regression that will let us predict y. Y's are zeros and ones instead of scalars now, instead of continuous values now. Same idea, we'll just fit a straight line and make our predictions. We'll pretend it's a probability, and we'll have a threshold of 0.5. There are some small problems, like the first one is that you'll make out of range predictions. So like a straight line fit through any space will go on forever in either direction. And if you're trying to say that your predictions are predictions of probability, then you'll have infinite probabilities, you'll have negative probabilities, things that don't make any sense. This relationship's also nonlinear, so it's not like you just kind of gradually increase the probability as you move along these features. You're going to have a boundary between cases, and it would be much better to have a decision curve where we have things that are obviously 0 and things that are obviously 1. Cases that are obviously labeled negative and cases that are obviously labeled positive. And there's not just a smooth linear function between those two cases. So the linear function might be too much of an assumption. We have things called heteroscedastic errors. This is maybe not too important for the practicality of this course, but this refers to the variance of errors and how the variance of errors is not constant across the various features that you have available in your feature vector x. And then you also have the fact that the classes and costs are not symmetric. So right now we have a binary case, but even in a binary case, as we'll see in today's module, you'll have costs associated with the negative class and the positive class that are different from one another. You might have many more examples of one or the other, and you need to take that into account, which quite frankly will be a problem for us later anyway, but I'm just mentioning it now. It doesn't make sense. Having a linear function doesn't make sense. Point final. So we want a model that still produces outputs that are just bounded from 0 to 1, because the model is going to be giving us probabilities, right? The whole model is supposed to be giving us this, the probability of a true class label. So it needs to be probabilistic. If it's probabilistic, then we can interpret it like a probability, and then we can, because it's a probability, we could combine it and we could decompose it in a way that we would do with any other form of likelihood or long likelihood, which will be important for us. So given a model that will predict that a given input x should be labeled as y equals 1, the positive class, there's 2 steps. The first step is to basically do linear regression. Everything I said before, notwithstanding, we're still going to pass our input x through a linear function. We'll still do a linear regression with our parameters, which I called beta previously, and now are called w and b. This will produce a number z. But then I'm going to pass z through a nonlinear function that will give me all the good probability-ish goodness, or probability-looking goodness that I mentioned. It's going to be a function on 0 to 1. It's going to behave like a probability. It's going to be nonlinear in the right ways. So this is a sigmoid function, which is here. I'm almost never going to ask you to memorize this function, although it's quite easy to memorize this function if you want. It takes as input z, which is the output of this linear regression over here. And then this is just a form of it. It's 1 over 1 plus e to the minus z over here. There are some variants of this where we have extra parameters that can stretch and move the function I'm about to show you around a little bit, but this is the fundamental default form. Sigma is one of those Greek characters that keeps on coming up in all kinds of contexts. Previously, sigma represented our standard deviation. Now it's representing the sigmoid function, and it's representing the sigmoid function because sigma and sigmoid are both refer to the same shape, which is kind of an S shape, which we'll see in a moment. So the probability that a given observation X belongs to class 1, it's just the linear transformation of our inputs X passed through this nonlinear sigmoid function. And that'll give me a probability of 0 to 1. The probability that this is class 0 is just 1 minus that probability, right? This is kind of like the Bernoulli case. The probability of it being class 1, if there's only 2 classes, must be 1 minus the probability of it being class 0 and vice versa. So this will allow us to kind of fit as you'll see in a moment, a region which acts like a hyperplane that separates the 2 classes, all the data points from class 0 and all the data points from class 1. It'll basically form a hyperplane, a big cliff between these 2 classes. And, if you're very far from this decision boundary, then your estimates will be very confident that those data points far away from this decision boundary belong to one class or the other. But as they get closer and closer to this decision boundary, it's going to be harder and harder to be really certain that this data point should belong to this class or the other class. So this is a visualization of what I'm talking about. Here is just a 2-dimensional task. So we have x1 and x2. That's these 2 axes here in this graph. Every data point is just a data point with the 2 variables, x1 and x2. So here this is minus 1.14 and minus 1.87. That's the input, that's the data x. This data x is labeled as class 1, purple class. And then everything on this side of this red line, this decision boundary, is purple class. Everything on the upper left is class 0, turquoise class. So this is what I'm talking about when I'm talking about the decision boundary. I've kind of color-coded the region here. So as you get further and further from this decision boundary, you can be really sure, like, this is definitely class 1. Look how deep into class 1 territory this is. Similarly, if you get far from the decision boundary on this side over here, you can say, well, this is definitely class 0. Look how far it is from my decision boundary. Like, there's no way this is a purple X or a class 1 data point. But as you get close to the decision boundary, it gets harder and harder to be really certain of these decisions. Like this little class 0 over here, it's so close to the decision boundary that if I just had added some more noise, or maybe removed the noise that might have been added to this point, maybe this data point would have been on the other side of the decision boundary and would have been classified the other way. So it's a bit challenging, but this is basically a fundamental idea in discriminative machine learning. So all of these x's, x1 and x2, I pass those into my little regression over here. So I have some values of w and b that have been optimized, and they give me a value z. And that value z is down here on the x-axis. It's on the z-axis technically. It's a bit hard to see here, but this is the value of z. And it'll be passed through the sigmoid function. This orange curve is the sigmoid function. Okay. And so it's called sigmoid. Sigma is S, and it's kind of S-shaped. So you can kind of see here, or you can see a hint anyway, that the sigmoid function is bounded below by 0 and above by 1. Just like a probability will never be less than 0 or greater than 1. So for any value of z, you're going to get something between 0 and 1 coming out. Positive values of z are going to give you values of coming out of sigma that are above 0.5. So any of z that is positive will classify as class 1, and anything below, any negative z will classify as a class 0. So this curve basically is still the probability that what I'm observing is belonging to class 1. So, you know, the z's that basically represent like the distance between these points and the decision boundary. Like these points that I'm pointing to down here in the lower right will have very big values of z, be very far to the right of the second graph, and therefore the probability of them belonging to class 1 will be very high. Similarly, in the upper left-hand quadrant, these values of x will result in very negative values of z, which will give you a very small probability of these data points belonging to class 1, as indeed we want. But, by this reciprocal thing, 1 minus this very small probability will give you a very high probability of them belonging to class 0. So hope that's clear. You can play around with this a little bit, although there's not very much to play around with. I think you can turn on and off these, for what it's worth. So probabilities are something that we never can truly think we understand completely. We always have to be curious and keep on learning. So this is something that people kind of fall into a trap to think that they know what probabilities are. Imagine you train a model for hospital readmission in 30 days. Should this patient be sent home or not? If they're going to be coming back in a week, then why even bother? We should keep them in the hospital. So we can compute these for every patient we have in the hospital. We can sort the patients by the predicted probability that they'll be coming back in 30 days if we send them home. So we can take the top 10 of these probabilities and we can label them with the class high risk. The top 10% of these patients, in terms of the probability of coming back, those are the high risk cases. So we've kind of we're not dealing with a decision threshold anymore. We're doing labeling at this point. We have all of these probabilities, and we're just saying, well, top 10% are very high risk, so we're done. 10% came out of nowhere, but seems reasonable. A policymaker, or maybe a CEO at the hospital, might say something goofy like, these probabilities are exact. If the model says 0.8, that means exactly 80% of these people will come back. And that's one of the things that people get wrong with probabilities amongst dozens of other things. These probabilities are estimates. They're estimated from data. There's all kinds of other confounds that can go into these estimates. They're never perfect, and it's not a guarantee that exactly 0.8 times the number of wait, this is totally off, isn't it? Yeah, this is fine. 0.8 is if the probabilities, if the model says 0.8, there's a 0.8 probability on these patients that exactly 80% of them will come back. So this is an anti-example, as the title suggests. These probabilities are estimates. There's uncertainty built in, like I mentioned a moment ago. Calibration can matter. So this can mean, we expect about 80% to come back. On a big sample, if you measure, across the entire sample, normally there'll be around 80% of the population that'll come back before 30 days. With the regular caveats that we saw in the previous modules around bootstrapping, with those means of means, there's going to be a range that we'd expect. You can't say it's exactly 0.8. That's the first message. The second message is it doesn't mean anything about an individual person. The probabilities are about sampling groups in aggregate, not necessarily about individual members of that group. Although sometimes we can apply the probabilities across those different concepts without loss of generality. We can't always do that. And again, something might be wrong with the model. I wouldn't stake the reputation of the entire hospital in this kind of claim. And the regular caveats about over or underestimating risk for certain subgroups. Again, this is a research area in healthcare. Never mind machine learning, but there's lots of evidence that certain demographic groups are discriminated against. So these probabilities can be useful signals, but they're not crystal balls. You shouldn't take them as an oracle. And you always have to keep them in the context with which they were derived. I'll mention this this is another example, beyond hospital readmission, but just in terms of risk of precipitation, which I think more of us are familiar with than hospital readmissions. There's all kinds of ways in which people misinterpret the probabilities that come out of their phone when they talk about, there's a 60% chance of rain today. Some people say, well, that means it's going to rain for 60% of the day. Some people think that means the intensity of the rain is going to be 60% of the overall intensity. There's other possible ways that people can misinterpret those probabilities. They also can say that, well, imagine if there's an 80% chance of rain and then it doesn't rain that day. I think a lot of people will say a lot of these predictions are meaningless. It said 80% and it didn't even rain. And they can't seem to understand that, well, there was a 20% chance that it would not rain, which is still pretty high. 20% can be high in some contexts. and it didn't rain. So you happen to be in the world in which you sampled from that 20%. It doesn't mean that the 80% estimate was wrong, right? That's a really key idea that everyone doesn't seem to understand. When I say everyone, I'm speaking very loosely, obviously. Anyway, off we go. A little bit of math, not too much though. So here's the sigmoid function. This is under the microscope, so don't worry about this too much. So here we have our sigmoid function. We define that as is defined. This is the sigmoid function. We are acting as though the outputs of the sigmoid function is an estimate of probability, and we do that if we pass in the regression, the linear regression that we talked about previously. These can be expressed as sort of the odds of something happening. So the odds of a positive class Y is sort of the ratio of the positive class to the negative class. It's like p hat is our estimate for the probability of the positive class, and here it's normalized, or the denominator is 1 minus that probability. So it's just the odds of one to the other. Often, when you're introduced to probabilities, maybe even in first year, they're kind of expressed more or less in these terms. We're not going to talk too much about examples like this, but I just wanted to just touch on this because this is something we see sometimes. So log odds, as the name suggests, is just the logarithm of this ratio. And for reasons which I won't get into right now, if you work it out and write out these values of p everywhere and express things in terms of sigmas, and you can, if you have nothing else to do, you can work this out for yourself, but the log odds ratio turns out to be the linear regression that we were feeding in the very first case. So logistic regression basically makes the log odds estimate of a linear function of features, which is kind of what we wanted in the first place. So the way to interpret this is that, well, every coefficient, w sub j of feature j, will tell you how much the log odds of the positive class prediction will change when x sub j increases by 1 if you hold everything else fixed, right? So if you're doing actuarial science or the kinds of statistics that you see in areas like typically finance or economics, they tend to do this odds and log odds more commonly than we see in pure machine learning. Just wanted to touch those two universes together. But again, this is just still a side note. Training logistic regression is a little bit beyond the scope of this course, this first year practical data science class, but I want to touch on it anyway. The parameters that we can change are W and B. So W and B are the coefficients we can adjust in a linear regression. And this we'll try to make our predicted probabilities as close to the true labels as possible. So we can try to maximize the likelihood. This means, if we maximize the likelihood, this means minimizing the logistic loss. So if every example comes with a label, either 0 or a 1, y is either 0 or 1, then we have a predicted probability function, which is just the probability that y equals 1 given x. Then the function we're trying to minimize, again, we're going to frame this within the same kind of gradient descent mechanism that we've seen previously. This is quadratic, or it's nonlinear in the right way, so we can still optimize in more or less the same way by minimizing a loss. So in this case, the loss we're trying to minimize here is negative of the logs of both of these possible conditions. I'm going to try to go under the hood a little bit, but I'm going to try to be kind of brief. So if you have again, this is just looking at an individual data point. So we're not computing the overall risk on average of an entire training data set. Now we're just looking at how badly we predicted a particular data point. We have a particular data point with output, which is actually y, 0 or 1, and we have a prediction of a probability being p hat given x. Okay, how well did we do? If y was actually class 1, so it was a positive class, y is equal to 1, then we keep this term, y is 1, so we still have log times p hat. But if y is 1, then this second term disappears. 1 minus 1 is 0, and this entire term disappears. So, and we have these two terms here, one on the left here and one on the right. These two terms basically refer to the case that y is positive and the case that it's negative. So if it's positive, we keep this first term, like I mentioned a moment ago. If it's the other way around and y should be 0, then this term disappears. It's not the positive case. We're over here on the second term. 1 minus y equals 0 is 1, so we're left with log times 1 minus p hat. And then you can tell how close p hat is to the truth. Okay, if p hat is, if you're in the positive case, and p hat should be as big as possible, so log p hat should be, like, again, log increases with its argument. So if p hat is big, log p hat should be big, and that should be as big as possible. Similarly, if we're in the negative case, y is 0, the probability of x being part of the positive class, which we defined over here, should be as low as possible. So p should be as small as possible. So we're looking at 1 minus that. So we want p to be as small as possible. 1 minus that very small value p hat will give you a big value still. So whether you're positive in this term, like the y equals 0 case, or you're negative, y equals 0 in this case, in both cases, you want the probability essentially of y equals 1 or y equals 0 to be as high as possible. So we're good, but we want to minimize this loss function, so we just take the negative here because we're minimizing things. Okay, so you want the minimum value possible. So if p gets bigger and bigger, then you're dealing with more and more negative values, and then therefore you can minimize by maximizing the value of p hat. And parentheses, that's why this function exists the way it is. This is sometimes called cross entropy for reasons that also exceed the scope of this class, but this is the cross entropy loss function, which is used for binary classification of this type and other types. So yeah, I think this is basically like, if you can walk through what I said before, or you can listen to what I said before by looking at what's written down here. This explains what I explained a moment ago. In practice, this is all handled for you. So like you can just go ahead and just click on this link and read some documentation and just write the logistic regression function, as you'll see in a few moments. And you can just use it without knowing what's going on under the hood. But if you don't know what's going on under the hood, it's going to be hard to fix your car, so to speak, and you're going to rely on other people to do your work for you. Why not service your own automobile and be your own expert and learn what's actually going on? So we're going to want to not just evaluate these models, we're going to want to interpret what's going on, which is why we're kind of digging under the hood. I can't emphasize that enough. You always want to learn more and more no matter what. So again, another little stretch. We can go from linear regression to logistic regression. So for linear regression, we assumed that the true nature of the world was this linear relationship. So it was some coefficient vector w times x plus some bias b. And then we had some real world noise epsilon from the world, and that noise can be assumed just to be some Gaussian noise with a mean of 0. So it fluctuates around whatever the predictions are. This leads to the ordinary least squares scenario we've been talking about for the past few modules at this point. For a binary value of y, a normal error model won't actually fit well. We want y to be 0 or 1, on this range and probabilities. There's no continuous noise to deal with. So instead of this kind of normal distribution, we're going to deal with the Bernoulli distribution. So you might recall that the Bernoulli distribution has one parameter, and it's basically just the parameter that the observation comes up positive, the coin flip comes up heads, so to speak. And we call that p hat. So we can model p hat using this logistic function, which we defined a moment ago. And we know we can because now we have the probability of data point input x belonging to class 1 basically is p hat, and the probability that it's class 0 is 1 minus p hat, which follows the Bernoulli distribution. Maximizing the likelihood of the observed labels will give us our logistic loss, which we defined previously, and this will make logistic regression basically a kind of generalized linear model. Actually, so I'm not really saying anything new here. The only thing I'm really telling you here is that framing this linear regression through the sigmoid function and turning everything into a probability distribution basically turns things from like making predictions on a scale using Gaussian noise to making predictions in a Bernoulli scenario where you're essentially flipping a kind of weighted coin and making predictions on a binary classification task. Let's take some examples. So the first example will be trying to detect whether a tumor is malignant, that is to say cancerous, or benign, not cancerous, in breast tissue. This comes from scikit-learn. So there's tons of features. This is a table. There's not imaging here. So it's like things like mean radius, texture, perimeter area. These are all factors that matter to a breast cancer prediction. So just, and we'll have measures of smoothness, compactness. We have a lot of features. So we'll have a label. The label will be malignant or benign. So y equals 1 or y equals 0. And we'll train logistic regression to optimize those W's and B's we talked about a moment ago to make as accurate predictions as possible. So first, we'll just load the data set. We'll split the data set into training and test or validation. We'll fit our model. It'll be done under the hood for us. And then we'll look at metrics like accuracy, and we'll look a bit more deeply with confusion matrices. So here's just loading the data. The data here come from sklearn. So this is a function called load breast cancer, which we go ahead and call here. It's loaded as a data frame for what it's worth. And we split it up later, it looks like. Yep. So this is just the raw data. So here's like the first 5 rows, and here's a bunch of values of those various columns I mentioned earlier. So this is where we do the train test split. We have 30% for validation. We have a random state. We do stratification, just making sure that the balance of positive and negative cases is more or less consistent in the training set and the test set. So it's stratified according to Y. That's our class label. And then we have our pipeline. Our pipeline does our scaling, because we learned from the last module how important scaling is. And then we'll do logistic regression, and logistic regression is iterative, so it'll do like gradient descent. So we'll do like at most 2,000 steps. That's our definition. Go ahead and fit our logistic regression to the scaled data. Make our predictions, please, and then tell us how well we did. And then report it. And the reporting tells us that we got 97.1-ish% of predictions accurate. Sounds pretty good. So we want to dig into our results a little bit deeper than just mere accuracy. There are 4 conditions we can be in when we're making predictions in this binary classification task. So imagine the positive class is malignant. Well, the data point can actually be malignant, and we could have predicted it as malignant. This is a true positive. Okay, it's a positive class, and we've identified it truly as such. It could actually be a malignant data point. This could actually be breast cancer, but we could have predicted benign, so we made a mistake. What kind of mistake is it? Well, we called it negative. So if the positive class is malignant, then the negative class is benign. So we called it negative, but that was wrong. So we called it negative, but that was false. So we call this a false negative, or FN. It could have actually been a negative class, so it could have actually been benign, but we could have accidentally predicted it as malignant. So this little quadrant says, well, we labeled it as positive, as malignant, but that was false. So we falsely said it was positive, so false positive. And finally, the only other condition we can be in, well, it was benign, and we predicted benign, so we called it negative, and it truly was negative. It was a true negative, and this is true negative. So now we have these 4 different extra little sub-metrics we can think about. We can come up with a few different metrics. So accuracy is just basically the sum of all of the instances we've observed along the diagonal of this matrix, divided by all of the observations we've seen. So we count up the total number of true positives, the total number of true negatives. That sum is the total number of cases we got correct, and we just divide by the total number of cases across all 4 conditions. That's our good old-fashioned accuracy. Sorry. I'll fix this before I post this. I actually just fixed a couple of these labels a moment ago. I copied this from my machine learning class where we had the same slide talking with a fraud detection scenario. So fraud is going to be malignant in a few moments. I'm going to say malignant instead of fraud here. how precise were we in predicting malignancy? Basically, what we want is to take all of the examples of predictions of malignancy and see how many of them were actually malignant. So that means, like, out of all the things we predicted to be malignant and were true positive, and all the things we predicted to be malignant and were not, all the false positives, what proportion of those were just true positives? Recall is very, very similar. It only differs in one term, which is we swap out false positive for false negative. Here we're trying to say, out of all of the things that actually are positive, that we should have classified as positive, how many of them did we end up classifying as positive? So again, we have the true positives divided by the positives that we got right, down here, the TPs, plus the positives we got wrong, the false negatives. See, these were actually malignant. That gives us the recall. How many malignancies did we actually recall? There's this other number which kind of combines these things. So there are different costs associated with each of these different measures. So you could train a system to be highly, highly precise, but that might come at the cost of recall. You can train something to be have a very high recall, but that would come at the cost of precision. And sometimes you want to raise both recall and precision at the same time. How do you do that? Well, you can take the harmonic mean, which is just the product of those two measures divided by their sum times 2. And we'll leave this here for now. The way that I learned this is just to write it out 1,000 times until it becomes muscle memory. But we'll leave it for now. Just know that a high F1 score is good and a low F1 score is bad. So what should our intuition be? This is a nice way of thinking about things. This comes just from Wikipedia, but it's a really nice visualization. Precision basically means if we flag something, how often are we correct? And recall means of all the things we should have flagged, again, I'll fix this fraud to malignancy, how many did we catch? Okay, so precision basically looks at this circle. The circle says, these are all the things that I said were true or positive. How many of them were actually positive? Well, it's just the proportion of all the cases in this circle that are true positive, which are green, which you can kind of visualize down here. Recall is this whole column over here. So these are all the things that are actually positive. I got some of them correct, which are inside the circle. I got some of them incorrect. I called them negatives, falsely. But then the sum of all of these things is all of the things that actually are positive, and I look at the proportion of all of those that I labeled as such, and that's the recall. Now we can go to our confusion matrix. This is something I didn't copy and paste from my other class. This is how well we did. We got 97 or so % accuracy, and that's reflected pretty well here, right? So most of our cases are along this diagonal. We had 62 malignancies classified as malignant. We had 2 malignancies classified as benign. We had 3 benign cases classified as malignant, and we had 104 benign cases classified as benign. So everything looks really good here. In the future, we might see confusion matrices that are not so diagonal, but we want these confusion matrices to be as diagonal as possible. So yeah, I think we kind of went over this already. I'll just highlight a few things. So I mentioned that there's different costs associated with different errors. This is another one of those fundamental things that I hope you take away with you going forward. You know, on paper, these are just numbers. Looking at this confusion matrix, you know, this 2 and this 3, and they're close to each other, so it helps, but they just look like numbers on paper, so who cares what they actually mean? In this case, a false positive means that, well, someone, you think they have cancer, but they don't, so you tell them that, you send them for extra tests, you send them to a specialist, and it costs them a lot of concern. It costs them time to go get tests. It costs the hospital money and resources to do those tests, so it's this cost associated with a positive case. There's a negative case where you think someone has cancer, does not have cancer, you send them home. Maybe, you know, the costs for that are very human-centered, and if that person can come back to the hospital at a later date, treating them will be just costlier for the hospital also. So it's bad all around. So generally, false negatives in this case would be far more costly than false positives. That's the calculation that a lot of hospitals have taken, at least ones with free and open healthcare systems, like in Canada. And like for-profit countries, who knows, might think different things, but healthcare is a right. Anyway, take that into consideration. You have different costs for these different kinds of mistakes. So therefore, when you're doing your optimization, and you're doing your evaluation, you need to factor all of this into your processes and your analysis respectively. So, I mean, I went ahead, I think I did this occasionally, I answered one of these questions, but answer it for yourself. In this context, which error is more serious? Can you come up with another scenario in which the false positive and false negative costs are reversed? If you wanted to reduce false negative rates, what might you change? And there's a hint here also, which I'll let you read, I guess. I'm not going to say it because I'm tired of giving too much away. Second worked example. This is actually going to be about fraud now. We have bank transactions. A very small percentage of them are fraudulent. But the overwhelming majority of them are legitimate, but we want to find the fraudulent cases. So we want to train a logistic regression model to predict, is this fraud? Yes, 1, or no, 0. So I'm going to try to show you why accuracy can be misleading. This is kind of the lesson you're going to learn. And we're going to look at an implementation of precision recall in F1. So this is all going to be simulated. Here's our simulation. This is a lot of detail here. Like, there's nothing new going on in terms of our implementations here, except maybe 2 things. So this is our true probability model here. So I'm not doing anything new here. It's just that I'm setting a couple of parameters here. These are the true values of which I called beta in the last module. I'm calling them W now. These are just the coefficients that I want to be able to learn, but these are here specified by me that this generates the true data. This is the bias term. This kind of just changes how biased the model is. This is called B in this module. Everything is passed through the logistic function, the sigmoid function. The sigmoid function is 1 over 1 plus e to the minus x, and that's exactly what we have here. Again, I've mentioned this before, and I'll mention it again. Math and code are the same thing, and if you want to be really good coders, you need to learn your math, and if you want to learn the math, you need to learn the code. And if you want to understand the whole system, you need to understand both. Regardless, here is our just a description of how much of our data is actually fraud. So the Y is our class labels, our 1s and 0s. If we take the average of that class, it's kind of a little hack. That gives us the proportion that is positive class, and we see that, well, about 4.15% of all of our data in this simulated situation is fraud. So relatively small amount. So we can pull precision recall in F1 and use them automatically from sklearn's metrics library. Again, we will split our data into 70% train, 30% test. We'll stratify, so our frauds are more or less balanced between training and test. We'll call it logistic regression. This time we'll only iterate for 1,000 steps. We'll fit it. We'll make our predictions on our test case or a validation set. And then I also want to describe probabilities. And what's coming out here, I have my accuracy score. So looks great. I'm getting by basically 96% accuracy in predicting fraud. So I'm done. I have a great model, correct? Well, no, because let's look at the precision and the recall and the F1 scores for my positive class, which is fraud. I get 0% precision, 0% recall, and 0% F1. That seems to be a bug, right? Is there a bug in my code? Like I'm getting almost perfect accuracy, but I'm getting 0 precision, recall, and F1. Something must be wrong. Let's continue anyway, just in case there isn't anything wrong.